Hello, ma'am. Good day. I am Godofredo Hipos Jr., and this is my output for the machine problem number 1 in Math 221 online, which is the numerical methods for ordinary and partial differential equations. I choose to implement the method Newton-Raphson, Newton Interpolating Polynomial, and Gauss-Jacobi method. Okay. So let me show you the interface that I use. This is PyCharm. I specifically choose this IDE because it is very neat and clean, as you can see, and it is very easy to use. So this is user-friendly interface, and what I like the most about PyCharm is that it doesn't take up a lot of space in your drive when you install it. And yeah, it do have a lot of powerful features that you can use when you are programming, and it is user-friendly overall. As to the language that I use Python because I know that Python is one of the easiest programming languages out there. It is very easy to understand because, as you can see, it is English-like structure. And also, Python is very approachable. Even if you doesn't take up computer science class or you are not a programmer, you can still do a lot of tools in Python. And what I like about Python the most is that the community of Python is very active. That means that you can get a lot of support from the community once you encountered a lot of troubles, especially along the way when you are programming. And having a very well documented language is one of the best aspects if you are a beginner in the field of programming. That's why I choose Python. Okay, so I will now explain the methods. Let us first discuss about the Newton-Raphson as to how I implement the Newton-Raphson in Python. Okay, so Newton-Raphson. As you can see here, I imported libraries that I use, which is the NumPy, SymPy, and the Tabulate. This will help me ease up a little bit in the programming, especially in finding the derivative of a function or presenting the results in a tabular form. So this will help me a lot. So SymPy is used to get the functions and also its derivatives, and also the value of a certain function given a value of x. And the tabulate is used for showing the results in tabular form. Okay. Here, I declared the tolerable error, which is 0.00001. Okay, this will help me to track when to terminate the loop. Okay, then I use the symbol x as my variable all throughout. Okay, and here I displayed the header. Okay, this is not Newton-Raphson, so let me change it to Newton-Raphson. If I run this one, this will print out the header that says Newton-Raphson method. Then it will start the loop. Okay, this is the loop for finding or asking for the function. The function is in string format. Okay, asking for the input. And then that particular string is converted into symbolic mathematics. So this method, simplify, this will allow me to convert the string input into symbolic mathematics and then stored to fx simplify, which is just a variable. And if the function is having an error, so for example, the library cannot read up the function well because there are syntax errors. So probably this will print out the invalid equation. And if an invalid equation occur, then it will ask for another input again. Otherwise, if everything is good, then it will break the loop and start the next process. For the next process, we have also a while loop. Then it will ask for an input, your initial guess. I use double data type. Double data type is somewhat similar to the float data type. It will consider floating point numbers. And if your input is not in double data type, so for example, you inputted special characters or letters, then it will print out invalid input. And if everything is good, then it will break the loop and start the new process. Here, this function will get the derivative of the fx simplify, which is your equation or the given equation, and it will get the derivative of that one just by having that diff using also the variable x. It will stored in fx derivative. Then after that one, I declare the initial conditions. I have iteration set as x, and then the matrix is blank. So here, this will be the matrix, or this will be the variable where the table is stored. Later on, we will fill up this matrix. And here I have started the loop for the iterations of the Newton-Raphson. Okay, so I started counting iteration. Okay, this will be a counter for my iterations as to how many iterations are overall in the program. And here I do substitution for the function, given function, using the variable xn. Okay, and then also I do the substitution for the derivative also using the variable xn. And then after that is I will get or calculate the new value of x using this formula. And then I also get the percentage of error using this formula. Okay, then after that one, I used a dummy array. Okay, so this will represent each row of the table that I will show you later on. So I considered saving the iteration, the number of iteration, the value of the x, and then the function a of the derivative also, and the new value of x, and then the error. Then after that one, okay, it will be appended to the matrix. Okay, that dummy array is then appended to our matrix. It will be added here, and then start a new loop, okay, using the new value of your x as your current x. And after that one, it will check for the error. If the error that you get here is less than the tolerable error that you set here, okay, if it is true, then it will break the loop. Otherwise, it will continue to loop or to iterate and then get another row for that one. Okay, once the loop is being terminated, then all the values that you want is then stored in our variable matrix. So here I tabulated the result so that it will be presented nicer in the output here. So matrix, I put up headers. So the header, we have I, xn, fxn, f prime of xn, and then x plus 1, and then the error. And then the result is then rounded to 5 decimal places. So let's try. For the purpose of this validating the program, I will use the exercises or these example exercises that we do in module 1. Okay, this one. We check if this is Newton-Raphson. Okay, this is Newton-Raphson. So I will use this as an example so that the table will be compared to the one that is being presented here in the output of the program. This is the function of x. We just input this one using symbolic mathematics. So we have 0.7 multiplied by the variable x. So multiplied by the variable x. And then multiplied by 1. Okay, let me put parentheses for that one. 1 minus the e, which is in symbolic mathematics is exp. And then raised to the power of negative 143.08 over x. And then let's close this one and also close this parenthesis. And then minus 52.7564. This will be your function of x or the given equation, and it will automatically, the program will automatically get the derivative for you using this line. Where is it? Using this line. Okay? It will automatically get the derivative for you. You just need to press enter. And then after that one, okay, it will ask for the initial guess. The initial guess would be, in my example, I use 10. You just put 10 here, then press enter. After that one, it will display all the necessary information, especially each iteration of the Newton-Raphson. So let's compare it to the one that I have here. We have 10. Okay, I think everything is good. Okay, I think everything is good. Yeah, everything is good. And after that one, okay, once the error is less than the tolerable error that we set first, which is 0.00001, you can display the value of your x, which is the final value holding the variable xn. This one. Okay. For this problem, I subtracted 5 kilogram because it has 5 kilogram as the weapon. For this one, I did not subtract 5 kilogram because this is the original method. Okay. So I guess that's it for Newton-Raphson. Let me now proceed with Newton interpolating polynomial, which is the second method that I use. Okay. For Newton interpolating polynomial, I use the library ordinal so that I can use first, second, and third. Those are ordinal numbers. And also tabulate for the presentation of the data later on. So for this one, I will start explaining in the main function. Okay? So for me to track, since the program or every programming language started finding the main function, and then the program operates in the main function only. Then all the other functions will then be called in the main function. Okay, so let me start in the main function. In the main function, I created a data list, which is just an empty array. Okay, this will then be used to store the numerical coefficients of each equation. And then it will ask for number of data or the number of equations that you are going to use to solve for using Newton interpolating polynomial. And then the data type is integer. After that one is we have a loop. Okay. If you inputted 3, then this will loop from 1 to 3. Okay, then asking for the numerical coefficients of each equation. Okay, so you need to enter the data. Then, okay, I use split because for this example, I am using multiple inputs per line. So I will split it up so that I can get each individual data. Okay, and then those data are then appended to our data list. Okay, if everything is good, then you don't need to worry. Otherwise, it will print invalid input. Okay, here we have columns. So this is in preparation for the table. Okay, this is the header. We have X and Y, and then extended with the ordinal numbers. We have first, second, and third. So I will show you this one. Let me just run this one so we can visualize the lines. So for example, here we have a function of X. No, this is not the method. Newton interpolating. Newton interpolating. Okay, so asking for data. Let me see the example that I have used. It's number 14. Okay. So this one, we have 7 datas. So that would be 7. Okay, and then it will ask for the each row. So multiple datas at a time. So we have 5 and 5.025. 5 and so separated by a space. Otherwise, the program will not recognize your input. 5.02375. And then we have 10 space 41.095. And then we have 15 space 25.8762. Next, we have 20 and then 34.78. After that, I have 25 and 40.4675. Okay. And then 30 space 10.355. Okay. Then we have 35 space 4.10125. Okay. Okay, so this particular line here, it's here, and yeah, it's good. Okay. Here, as you can see, I prepared the header for the table that I am using. So we have X and Y. So you can see here X and Y, and then all the ordinal numbers from 1 to N. So if you inputted 7, then from 1 to 6 data. Okay, then first to 6. Okay, so how the Newton-Raphson work? So as you can see here, I've prepared the for loop. Okay, and also, okay, so this is nested loop. You range from 0 to 1 and then it started from 1. So for that, so this one, for example, so we have 5 and 10, or we have here for y. That's why it's added by 1. Okay. Then those lists are then, okay, those lists are then appended. Okay, but before it is being appended, this is a function called interp. Okay, so it will go to a specific line in your program calling the interp function right here, interp. So here, okay, these are the parameters that are being passed. We have the data list, and we also have the I and j. So the first two datas will then be passed here, and then, okay, I use memowise. So memowise is a function in Python that will help me to track for repeating inputs. Doesn't, if the input is already calculated, then it will not do again or do the operations again. Okay, so if I and j in memowise already, then it will automatically return the value. It doesn't calculate the, or it doesn't calculate the method again, but it will also it will just return the value of the memowise. If I is equal to j, means that the datas are being stored back to memowise and then return the memowise. But if it is less than 1, so for example, here, this is 0, okay, this is data 0 and this is data 1. So if I is less than to j minus 1, probably, okay, so probably this will be true. Okay, then what it does here is, okay, it will call the function, another function which is called func, this one. Okay, this, I have passed the parameters. Okay, this one, this one, this one, and also this one. Okay, those are the 4 functions that being passed, or the parameters that being passed, and it will then calculate the operation, which is using this formula. Then rounded to the nearest 5 decimal places. And then going back here, it will return the value here, and then stored to memowise again. Okay, so I used function calls because I observed that all the operations are being used using or being calculated using this formula. I only change the value or the value that I pass. So for example, in the second iteration, the value that must be passed is this one, these two values, and these values. So it will then, so for the another iteration, it will then pass the new values, this one and this one. Then solve again for that using this formula, and then start back to memowise again. So as you can see here, this is a recursion method, because as you can observe here, okay, I call another function, okay, okay, calling itself. So that is a recursion method. So to lessen up the method, okay, so I used okay. So next is okay, so everything will be stored to memorize the table, and then it will then be returned to the main function. Okay, so then return to where is it? Here. And then everything is appended, no? Every data, every data that is being calculated in the inter function is being appended to the data list that we have here. And then, so this table is now in the data list. And then we will just tabulate the result to make it look nicer. Then the data list and also the columns. This one, header, and then just print the table by ending with two line characters. So here, two new line characters. And then, okay, table is now done printed. After that one is, it will get all the um, values in the first row. This one. This will be used as B0, B1, B2, B3, B4, and so on. Everything here is then stored to this one. So as you can see, this particular function here, no, this one will get the displayed B0, iterate from 1 to n, and then these values are then converted to string for later purposes. Okay, so this data here is being converted to string for this function here. So the equation. I also printed out the equation, so yeah, I used string data type. Okay, and then here the equation is being, or the expression is being formed. Okay, so loop, just loop. Okay, first data. Okay, and then extended using the second data. Okay, using this one expression joining asterisk. Okay, and then the expression appended to our expression list so that I can get the entire expression of the um, interpolation. I could get um, the best representation, or the best equation that represents this data. Then, if the expression is good, then let's display the expression. Okay. So everything in the expression list is being joined and then stored to expression. Then just print out the expression. So this is the expression. In the example, this is the expression. This is just the raw expression. Okay, I used asterisk for multiplication. Okay, so that I can evaluate it later on. Okay, since the symbolic mathematics considered asterisk as multiplication. So in this example, I did not use asterisk anymore because I will not calculate that one. Okay, I manually calculate it. So for this one, I used the symbolic mathematic format. Next is, okay, we have to ask for an input from the user, okay, to predict the value of a function when you're, okay, so for example, if you inputted, this is 32.2. So for example, if the data is 32.2 or the value of your x is 32.2, then using this expression or using this function that best describes this table, okay, you can predict the f of x, okay, or the value of this one. You can predict it, press the enter, and then it will give you the value of your function when x is 32.5. So let me check if it is similar to the one that I get in my, yeah, okay, 5.75281. Okay, everything's good. And so what I did here is just a translation from the method that I used in the Excel file, and then just I converted it to programming language. I converted it to Python. Then everything is, I did not print this one because this is I get this one using manual calculation, so I did not print this one out. It would be very hard to code if I will simplify this one. So it would be very hard to code. And I guess this is good already, though it is very, lengthy. It still works good, even though if I do not have the simplified function. Just put the value of your x here and then calculate it. You can still get this one. Okay, I guess that's it for Newton interpolating polynomial. Let me proceed with the Gauss-Jacobi. For the Gauss-Jacobi, change it to Gauss-Jacobi. For the Gauss-Jacobi, I still use Simplify, Simpy from library. Okay, I imported everything and also the tabulate. So let me start again in the main function. Okay, this is the main function. Okay, first, as you can see, it will print the header and ask for an integer input. Okay, enter the number of systems or the number of equations. Okay, so if you want 3 equations, then you put 3 here. If you want 4 equations, then you put 4 here. Okay, and then it will create an array, right? With length, depending upon the number of equations that you want. So this will create a 2D array, two-dimensional array. And then after that one, so if you want 3, so it will create a okay, it will then create an array equalist. After that one, it will ask for the coefficients or the numerical coefficients of each variable using or following this format. So it will ask for x0 first, and then x1 first, and then to xn. And then last is the constant of the constant of the equation. So you still need to enter the numerical coefficients separated by the space. Otherwise, it will not be recognized in the program. Okay, so here, this is the loop to ask for each equation, or to ask for the coefficients of each equation, and then stored to EQU, and then, okay, and then, okay, the values are then split, and then stored to the equilist. Okay, but before that, the function or the values are being casted to the float data type, okay, for easier calculations later on. So, since the equation or since the input that being inputted here is in string data type, so we have to cast it to float data type first, so we can do mathematical operations later on. So for this example, I will use again the exercises. That's 9, Gauss-Jacobi method. Okay, so for this one, the number of system is 3. So as you can see, there are 3 equations, 3 unknowns. Okay, so then the format is in x0, x1, and so on. And then last is the c. So we will input 4, followed by -1, and then -1. And then last is the c, 3. Then ask for the second equation. We have -2, 6, 1, and then 9. And after that one, we have -1, 1, 7, and -6. Everything is good. Then after that one, it will display the tabular form of the inputs. Okay, this is the x0, x1, x2, and the c. Okay, where is it in the program? This one. Okay, so I created the header. So this is for the header. So you can see we have x, then a variable x, the variable I. So for I, 0, 2, the number of inputs. So if this is 3, so up to 2. And then also added with the last constant. Then the table is being then, okay, everything, these values are being stored in equilist. Okay, so tabulated, and also the table columns, the names for the columns or the headers. Then just print the table out, just like this one. And then after that one, it will ask for the tolerance value that we will be using. So you have an option of changing the tolerance. Okay, so for this example, I will use 0.0001, just like the exercises. And then you have just to press enter, and then it will call for the function Gauss-Jacobi to start the method, since all the inputs are being loaded already. So it will then pass the list of all the inputs, also the number of equations, and also the tolerance that will help us to track as to when to terminate the loop. Then it will go to here, our function, which is Gauss-Jacobi. This is the method. Okay, first, I still use the variable x as the symbol or the variable all throughout for this code. and I created an empty array. Okay, this will help me to save all the results later on. And then I created an initial array. Okay. And after that one is I created expressions. Okay. The expressions for each equation. Okay. Um, okay. So here we have, this is for if the index is -1, that means that that is the final element in the array. So that means that that's C. So simply getting the values of the C and then creating the expressions. So let me just print the expression later. I will print the expression so we can see how it looks like in the back end of the program. And I also set the initial value. So for the initial value, I used 0 since in the example, I used zeros as initial values for the x and blank naman for the errors. So this will help me to initialize the table. So that's why I choose none and then three zeros and then three nones. Okay. Then the method is here. So first, I get the expression. For the expression, for example, this one, this is 4 times x0 plus, okay, -1, x1, and then this is -1, x2, and then plus c. So let me print the expression here so that we can see what this look like in the program. Expression, and then let me rerun this one. So we can have a better look as to how the system operates. So I have used three inputs and then -1, -1, 3, -2, 6, 1, and 9. And then we also have -1, 1, 7, and -6. And ask for initial tolerance. So as you can see here, these are the expressions that are used in every iterations. So for example, this one, so that means this is 4x0. This is 4x0. This is 4x0, -1, x1, -1, x2. Okay. But all the values are being converted to float data type. That's why you can see a trailing 0 here. Okay, so this I use that one for better calculations of the values. Okay, then this one, -2, okay, x0, and then 6, 1, and then 1, x2, and then, and so on. That's just looping every now and then, so it repeats every 3. Okay, it's the expression for the given. And then, later on, we will substitute the values of our x0, x1, and x2 here so that we can get the value of that particular equation if you have. So we can get, for example, if my value of x0 is given and then x2 is given, so I can directly solve for the value of x1 by simply substituting the values of x0s and x2 here, and then solve for x1. So here, that's being being calculated in the next line, I guess. So here, this is the substitution for, okay, if you have, okay, so consider that if you are using for this one, if this is 0, so if 0, okay, for k is not equal to j, that means that for x0, you have to not calculate if j is 0 also. So you have to solve for x1. You have to give the x1 and x2 values and then solve for x0. So that's being solved in the equation here. Solve. So it will ask for, so let me just print the sub so that we can have a better look on the end program input. Again, 3. I have prepared one. Well, I can copy it, paste. First the notepad. And lastly, here. Okay. Those values are similar to the one that I inputted. Okay, so you can see, we can see here the each iteration. So we have for the expression first equation, okay, this one. If my x1 is 0, so initially it is 0, since it is initialized as 0, okay, from the start of the program, it's being initialized by 0, right here. Okay, so x1 is 0 and then x2 is 0. So solve for x0. That's why k is not equal to j. So 0 and then 0. If my x1 is 0 and my x2 is 0, so I can solve for x0. So just simply substitute the values of your x1 and your x2 and then solve for, okay, this one. This function will help me solve for the values of x0. Okay, given the values of my x1 and 0. So I can get the values of my x0 here. And then for the second loop, so this is equation 2. So you have to solve for x1. So given x0 and x2. So as you can see here, given x0 and given x2. So still 0, 0 initially. And then you can solve for the value of your x1. And for the third iteration, as you can see, I can get the value of my x2 using the values of x0 and x1. So as you can see here, still the values of my x0 is 0, and then the value of x1 is 0 again. Then I can use that one to solve for my x2. So using this function, solve for the values of the expression or the variable. Then in the second iteration, the values are being replaced with the new value. So as you can see here, just like in the table, where's the table? So you can see here in the table the value of your x1 be now 0.75. So as you can see, the value of my x1 is now x0 is now 0.75. Okay, just don't mind the trailing zeros because I used float data type. That's why it has trailing zeros. Okay, then for the value of my x2 is 1.5. So as you can see, no, x1 is 1.5. That's why x1 here is 1.5. And still do the same process again and again. And again and again. Until you can get all the values in here. Okay. Until such time that all the errors for the values of your the three variables are less than 0.0001. Okay, so where is it in the program? So again, I also solve for the errors. No, each iteration it has an error, so let me just comment it out for later. It will not print out again this one. Okay, so and also I solve for the errors. So you can see here in the table, I also printed out the errors. So once the error drops to the values that are less than the value that we set in the code, will now terminate the loop. Okay, so if the errors are less than the tolerable error, then it will break the loop. Okay, and everything is stored in the results. Okay. Then we will now ready to set up the table. We will now be ready to set up our table. So you can see here, I inserted values, and then I also prepared the headers. I named it columns, name of the columns. So we have K, and I also have X underscore, okay, starting with 0. So loop from 0 to how many values that you want, or how many equations. So that's why I used loop for that one, and then added with an extension of the error from 0 to 2. Okay. Then after that one is the values are being stored in TB. Okay. Then putting here column and also the num align. So I also consider the alignment of the numbers into the left side since the default is in the right side. So I use num align left. And also if there are missing values, so for example, here I used none, no, to initialize the table because since in the example that I used, I don't have values for this one. So if the values are missing, if the table values are missing, then let's put an dash here. So that's why you can see in the table that we printed out, we have a dash here. And after that one, okay, you have to print the table. So this is the output for printing the table. Then after that one is we will get the last last values of my x0, x1, and x2. This will be used as the final value of the method. So that's why you get the so enumerate the results and then get the final value and then loop it out so that you can print it like this. And that's it, I guess. So let me check if all the data's here. Let me input it again. So for reference, notepad. Okay. So 0.0001. Let me check if everything is the same in the example. Okay, I guess. Okay, I guess everything is good. Everything is similar. And then the values are 1.0, okay, 2.0, and negative 1.0. So I used floating points. Okay, so I still want if the final values are floating, so okay. So I guess that's all for the three methods that I implemented. We have the Newton-Raphson, Newton-Interpolating Polynomial, and Gauss-Jacobi. And thank you so much for listening, ma'am. I do hope that the program that I created is okay. Thank you so much. Have a great day. Bye bye.